So this is continuation from last time's lecture. So before we move to the concentrations, let's look at a few examples. This is from Harris's book. For example, if you want to convert meters, 1.7 10 to 4th meters to kilometers. So you start with your number, and so the goal is to go from meters to kilometers. And how can we do that? And the answer is by using the conversion factors. We know that 1 kilometer is 1,000 meters. So, and that is equality. And you can use that equality, you can convert it to conversion factor so that the meter is here. You see 1 kilometer is 10 to 3rd, which is 1,000 meters. So you put the meters denominator so that we can cancel it out, and what is left is 1.7 10 to 4th times 1 kilometer. So meter is gone, and so this is what you have, 1 point. So when you divide, of course, this 2, so that 4 will cancel out 3 of that, and now you got 1 left. So 1.7 10 to 1, so that means you multiply it by 10, it will be 14 kilometers. And the same way you can use convert the Pascal to Milipascal, and so from the prefixes, you know, the milli means 10 to negative 3rd here, and so we start with Pascal, and from the conversion 1 milli Pascal equals to 10 to negative 3 Pascal, and so you put it there, so that Pascal is here, they will cancel out. And so this will become, if you take the reverse of that, is 1,000. So you multiply this number by 1,000, or if you divide it by 0.001, you know, and then you come up with 1.9 10 to 1, or 19 millipascal. So that's the that is the example. So you can you can do anything. So this is another example in prefixes. You can always convert from one unit to the other. For example, if you want to convert kilocalorie to joules, we have this relationship between calorie and joules, so you can use that and to convert from kilocalorie to joule, kilojoules, whatever. And the rest I'm not going to go over the question here, but that is what we have. So let's look at the concentrations. This is Harvey's textbook. So the concentration is a general measurement unit that tells us about the amount of substance or solute in a known amount of solution. So this is the formula, generic formula, basically. So you got amount of solute, amount of solution. So of course you can, and there are different ways of formulas to show the amount of solute in a solution. The molarity is most common one, and also we got formality, and those two actually they tell you the same thing. If you look at his molarity here, and not that one, molarity and formality, you will see the same definition: moles of solute, liters of solution. The same here. It's just a symbol different. That means they give us the same information. It's just, you know, if you have glucose, you know, alcohol or sugar, you know, and when you dissolve it in water, they won't break down to their parts, to their ions. So in that case, the molarity and formality, they define the same thing. Basically they are the same. But when we dissolve an ionic chemical, calcium chloride, for example, or table salt, sodium chloride, as soon as we put it in water, they break down into their species, the ions. So in reality, we don't have any calcium chloride anymore once it is dissolved. What we have is calcium ions and chloride ions, and we cannot talk about molarity of calcium chloride because there is no calcium chloride as a whole in the solution. So that's why we mentioned the ions instead of the calcium chloride, but we say it anyway. When we say, for example, 0.1 molar calcium chloride, we understand it consists of calcium and chloride ions. But the formality, it is regardless of the type of species. So we can still call it 0.1 formal calcium chloride. It tells us that the whole thing. So that's the difference between the molarity and formality. So here we got common units of concentrations. Molarity, formality, we already talked about them. We got normality. It is N with equivalent solid. We will talk about that. And also we got molality with L, molality. It is moles of solute per kilograms of solvent. It's not the solution, it's solvent. Weight percent, grams of solute divided by 100 grams. Weight means it's a weight percent basically if you have 100 pieces, and so each piece is called in 100%. The volume percent, instead of grams, we can use the volume. If you have like alcohol and water, most probably we'll use volume percent instead of mass percent or weight percent. Weight to volume, we also, if we have solute, 1 gram in 100 mils of solution. So again, we can do that. Parts per million, if you have million a solution, then you can divide into million equal parts. So each part is called parts per million. And so this is definition. And when you deal with the formulas, this is basically how you can do grams of solute divided by grams of the solution times million. That's parts per million. How you calculate parts per million, and here is parts per billion. And again, if you slice something, a solution, into billion pieces, so each piece is called ppb, and the formula for that is, this is definition, this is the formula, grams of the solute divided by grams of the solution times billion. So the again, here we got normality. Normality is not used, it is not common anymore, but still it's better to know something about it. So you have normality. Basically you can find it by multiplying the molarity of the solution by N. So N here is dependent on the species you have. If it is HCl, it can give off 1 hydrogen, so N would be 1. If you have sulfuric acid, for example, N would be 2 because it can give off 2 hydrogens. If it is sodium hydroxide, N would be 1. If you're talking about the electron exchange redox reactions, then it depends on how many electrons have been donated or accepted. So you can find the molarity and then multiply by those, by the N number. If a solution, for example, let me see if I have, no, if a solution has HCl, for example, it is 1.5 molar, capital M, then your N will be the same molarity, 0.5 times 1, so that will be the same 0.5 normal. If you're dealing with sulfuric acid, for example, then N would be 2.5 molar, then your normality will be 0.5 times 2, which is 1.0 normal. The molality is, remember from the formula, it is the moles of the solid divided by the the kilogram of the solution. If we look at here we got one example, and so you see there we got molality, number of solid, moles of number of solid, kilogram of solution. A question: 10 grams of glucose is dissolved in 200 grams of water. What is the molality of the solution? Again, the moles of the solid, kilogram of the solvent. So make sure we're not confused there. It's not kilogram of the solution, it is kilogram of solvent. So here, the one with less amount is our solid, which is sugar. The water is 200 grams. That would be our solvent. And the first thing we do, we convert the grams to moles, and that, so here mole of glucose will be 10 grams divided by the molar mass of glucose, 180.16 grams per mole, and you come up with 0.55 moles. And the second step is you convert the grams to kilograms using this conversion factor. We know 1 kilogram is 1,000 grams, so gram is denominator here so that they can't cancel out. So basically you come up with 0.200 kilogram, 200 kilogram, and then you just plug in into the formula, and you come up with 0.28 molar. That is the exercise 1 sample question. So here the weight and volume, weight, volume, and weight to volume percentages. So you can always, it's straightforward. When we have a percentage, it means if we have, for example, 1.5% ammonium nitrate, that means 1.5 gram of ammonium nitrate in 100 mils of solution. So 50% means 50 grams of the solute in 100 grams of the solution. So that is also mass of the solute divided by the mass of the solution. And so let's work on this problem here. We have 25 grams of table salt is present in 225 grams of solution. And so what is the mass of the sodium chloride in this solution? What is the mass percentage of sodium chloride here? Again, the mass percentage is the mass of the solid divided by the mass of the solution times by 100. And so 25 grams of sodium chloride and 225 grams of the solution. Again, the 225 is the mass of the solution times 100. You come up with 11% of, so the solution is, so there's 11% of sodium chloride in this solution. Now, if we word this question differently, for example, if we say 25 grams of sodium chloride is dissolved in 225 grams of water, what is the mass of the sodium chloride in this solution? What mass percentage of sodium chloride? Now here, we're given the mass of the solute and the mass of the solvent, and so the mass of the solution, we need this mass of the solution to solve the problem. And to find the mass of solution, you add up those two, the mass of the solute and the mass of the solvent. So 225 plus 25, that's 250 grams. That's the mass of the solution. And then you put the numbers in the formula: 25 grams of the solute divided by 250 grams of the solution times 100. So you come up with 10%. So 10% of that solution is the sodium chloride. The other concentration units are parts per million. Parts per million is actually microgram of solute in gram of solution, or milligram of the solute in liter of the solution. If we want to convert ppm to molarity, just keep this in mind, because it is easier to go from milligram of the solute per liter of the solution to moles of the solute per liters of the solution. Similarly, parts per billion will be nanogram of the solid per gram of the solution, or a microgram of the solid per liter of the solution. Or, I mean, you can a microgram, or you see this microgram per liter. If it is a solution, of course, then we can use that one also as well. So again, converting between two, so you can always convert from one to the other. Now here, let's look at this question here. A concentrated solution of ammonia is 28% weight per weight of the solute ammonia and mass of the solution, and has a density of 0.899 grams per milliliter. So what is the molar concentration of ammonia in this solution? So here, what is given? If we look at the question, what do we know? What do we have? We have the concentration of solution, that's weight per weight, mass by mass, 28%. So that means if you have 100 grams of the solution, 28 grams is ammonia, the rest is solvent. And what else we know? We know the density. Density is given, that's grams per milliliter. And it's mass of the solution here per milliliter of the solution. So so what do we know? What can we do to solve this problem? So we have to start with something. The goal here is basically go from 28 grams of ammonia per liter of solution to moles of ammonia. That's the molarity. So we start with mass of the ammonia that is given here, 28%, 28 grams of ammonia per mass of the solution, and 2 moles of ammonia per liter of solution. So if we do that conversion, we find our concentration in molarity. So you start with, this is your starting point here, 28 grams of ammonia per 100 grams of the solution, and then using the density, first we will, before we use the density, we can convert these grams of ammonia to the moles of ammonia, so that we can convert grams of we convert grams of ammonia. We know 17.03 grams of ammonia is 1 mole. So now we got mole on the top, and then we use so far we got moles here, grams of solution here left, and then we can use the density. 0.899 gram of solution is 1 milliliter of solution. So now by using the density, this is continuation. By using that, you get rid of gram solution. Gram solutions are gone. The units are gone, and then of course we can we have a milliliter solution here, and then we use the relationship between milliliter and liter. We know 1,000 milliliter is 1 liter, so you put the milliliter on top so that you can cancel out the liters. So what is left is a mole ammonia and liter of solution. So the rest is just do the math. 28 times 1 times 0.899 times 1,000 divided by 100, and whatever number you get divided by 17, then you come up with your molarity, 14.8. Now the question here, how many sig figs do we have to keep? And if you look at the solution, the question here, your initial 28.0, that's 3 sig figs, so you have to have 3 significant figures in your answer. 0.899 also has the same number of sig figs. So again, you can do the same thing here. Another water supply is 2.50 10 to 2 ppm, so we want to convert that to molar concentration. Again, you start with ppm, and we know what ppm is. What ppm is a milligram of solid per liters of solution. So when you do the math here, you come up with 7.05 10 to negative 3 molar. So we have more exercises, so we have to we can work on more. The p function is another is a negative log. Sometimes we need to find the log. The p function, like pH, pCa, and so on, it is the negative log of the concentration. pH, for example, is the negative log of hydrogen concentration. When you take the negative log of hydrogen concentration, that will give you pH. It can also apply to any other ions. For example, if you have pH of 4.3 10 to negative third molar, you take the negative log of that, and it gives you the pH value 12.37. And for another question here, it says, what is pNa for a solution of 1.76 10 to negative third molar sodium phosphate? Now, we know the concentration of sodium phosphate. When sodium phosphate breaks down, it forms 3 moles, so you have to multiply that by 3. So again, it's basically the sodium concentration will be 5.23 10 to negative 3 molar, and then you take negative log of that, so you come up with 2.227. So you can do many calculations with that. The stoichiometry calculations, again, that is based on relationship in a chemical reaction, so you can do that. I'll leave it to another video, so we'll continue on this.